Also introduced the concept of differential geometry and statistics for the first time in this area. The result, known as RAO distance, was renamed in 2001 as VIBHUSHAN. According to HUMANOSPHERE, Japanese author, the idea of connecting statistics and differential geometry is too far away. However, we will not be Centenary allows the idea to be developed work also received his PhD under Fisher based on this one. Four more landmark papers in his career based on his work achieved. Some significant concepts from those papers include general class test of hypothesis, known as PROF.C.R.RAO score, and alternative to the Wilks likelihood ratio test and the Walls test, classical arrangements, present as orthogonal arrays, multivariate methodology in tests of significance and analysis of dispersion, now known as MANOVA, discrimination and clustering. Taguchi, the Japanese engineer who learnt about orthogonal arrays from Rao during his visit to ISI, popularized it as Taguchi methods used in quality control. Rao returned from Cambridge to ISI as he wanted to continue his focus on research and to develop the field of statistics in India. Rao became a full professor and head of the research and training section at the ISI. Rao found himself shouldering a great deal of responsibility at the young age of 28, but also realized that he'd been provided with a great opportunity to make a real difference. Rao developed a 4-year bachelor's program, the curriculum for a 2-year master's degree, and an advanced postgraduate 3-year training program. He began a PhD program in probability and statistical methods, first such attempt made in India. Being the only professor, Rao was the mentor for 5 to 6 research scholars at a time. To date, Rao has supervised over 50 doctoral students. Another significant event in his life at this point was his marriage to Bhargavi in 1948. Bhargavi, unlike many women at that period in India, was highly educated, with a master's degree in history and a bachelor's degree in teaching. She was his friend, confidant, and constant companion for 69 years. She was his most ardent supporter and, of course, the love of his life.
Good looking.
1953, Rao spent a year at the University of Illinois in Urbana as visiting research professor of mathematical statistics. He was exposed to the world of computers for the first time and attended lectures on the logic of computers and learned to write programs in machine language. While in Urbana, Bhargavi completed a master's degree in psychology, an achievement that always filled her husband with pride. The years at the Indian Statistical Institute were filled with prolific research activities, with extensive international travel to give lectures and attend conferences.
Dad was always an out-of-the-box thinker. That, I believe, led to his creativity and original thinking style. As a child, I used to go to him for help in mathematics, proving theorems. So Dad would go about proving it in an unusual way, and when I took it back to my teachers, he wouldn't understand one bit of it, and he always gave me a failing grade. After that, I never went back to him for help.
Probably the most famous thing he's known for is the PROF.C.R.RAO inequality. Justifiably. If you look at it from one point of view, it's a simple calculation. It's the consequence of something called the Cauchy-Schwarz inequality, and it's a very basic calculation. But I think of it as the right exercise at the right time, because what it did was it introduced some sense of optimality. What does it mean to have a goal, reaching the lower bound of that inequality? And it sort of sets, it was the beginning of setting standards on comparing procedures, one procedure versus another. And I think that it played a very important role in making statistics into a field unto itself.
It's thought of PROF.C.R.RAO as that he is more a scientist than a statistician. No, he made a huge impact on statistics, but if you look at his initial papers, a lot of papers in Nature and places like that, it's not a common place for statisticians. And so he always was a scientist who's trying to solve some problem. That's why I thought he was good. And statistical theories and methods came about in the process. And that's one way. He has touched almost every aspect of mathematical statistics applies to science.
Rao's contributions to research during this period were recognized by numerous awards. He was awarded the Shanti's Farooq Patnagar Cash Award. It was during the Sino-Indian War, so Rao immediately donated the Cash Award to the National Defence Fund. He then received the higher doctorate degree, SCD from Cambridge, based on his overall contributions to statistical theory and applications. Rao was also made a Fellow of the Royal Society in 1967, becoming the first Indian in his generation to receive the honour. In 1968, the government of India awarded him the Padma Bhushan, high civilian honour for his services to his country in the field of statistical education and research. Rao remained at ISI until 1979, serving in various roles: Director, Secretary, Jawaharlal Nehru Professor, and National Professor. He was soon to be 60, the compulsory age of retirement in India. However, chance played a role in what happened next. In the summer of 1978, P.R.Krishnaiah, a professor at the University of Pittsburgh, arranged for Rao to deliver a general lecture on campus. This lecture was attended by the Dean of Faculty of Science, Dr. J. Rosenberg. The following day, he offered Rao a job. Rao accepted, and in 1979, at the age of 59, he and Bhargavi moved to the US. Rao worked with Professor Krishnaya for the next 9 years to establish the University of Pittsburgh's Center for Multivariate Analysis. In 1988, Penn State offered him a professorship and the prestigious Epperly Chair in Statistics. Rao made the move to Penn State, as did the Center for Multivariate Analysis. Rao retired from active teaching in 2001 at the age of 81. He, however, continued his research activities as the Epperly Professor Emeritus and Director of the Center for Multivariate Analysis at Penn State. In 2010, at the age of 90, Rao moved to Buffalo, New York, accepting a research professorship at the University at Buffalo. He had published over 200 research papers during his 40 years in India and around 275 research papers during his 30 years in the United States. Rao has authored or co-authored 16 books, some of which have been translated into several languages.
Always a great admirer of Rao's. When I was a student, about 1965, the second edition of his linear statistical methods came out, and that was exciting to me. The first one was almost worn out from years ago, and it's a book that still takes an honored place in my bookshelf.
It's, the LSI book is not the first book you should read in this area. You read something else and then to learn the finer points, the more subtle issues, that's where you go for to get that kind of insight into those things.
It's really elegant.
Yeah, it's a really elegant book in ways that still surprise you. Even 70 years after it was written.
While Rao was recognized for his research work, his students have fond memories of him as a teacher.
Because the only reasonable book we had in statistics to learn anything from was Dr. Rao's book, Advanced Methods in Biometric Research. But it's really an excellent textbook in statistics. So we learned from that book. And it was always sort of a figure far in the distance when we work on that. And then when we came to Calcutta, I came as a research scholar, and so we met him, and he was very encouraging. Although I was not really working in statistics, I moved on to probability pretty quickly, but still he kept in touch with us. I would tell him what I was doing, and he was always very encouraging. He was a very good lecturer. I haven't read some of his lectures, and he's a great sense of humor when he lectures.
Rao had always felt that there was a need for an institute in India that focuses on high-level research in the areas of statistics, mathematics, and computer science. In 2000, Rao established a research institute in Hyderabad, the C.R.RAO Advanced Institute of Mathematics, Statistics, and Computer Science at the University of Hyderabad. The initial funds were from the government of Andhra Pradesh and a personal donation of $100,000 by his wife, Bhargavi. A few years later, the Prime Minister of India, Dr. Manmohan Singh, sanctioned 18 million rupees to expand the institute. The institute now has qualified staff to do research in cryptology, statistics, and biometry. The institute also conducts courses to organize at its conference various aspects of statistics. The institute also houses the C.R.RAO Gallery, designed by his daughter Teja Sweeney. The gallery showcases Rao's life and career. C.R.RAO has been honoured with numerous degrees and awards over his long career. He has received 39 honorary doctorate degrees from universities in 19 countries, spanning 6 continents. Some of his notable awards are the Samuel S. Wilkes Medal by the American Statistical Association, PADMA VIBHUSHAN, India's second highest civilian award by the Government of India, the National Medal of Science, the highest award in the US for a scientist, the International Mahalanobis Prize from the International Statistical Institute, the Indian Science Award by the Government of India for outstanding contributions to science. And finally, the Guy Medal in Gold from the Royal Statistical Society in the UK.
Is sound coming?
Able to hear you?
You are able to hear me. Krishnamurti is able to hear me, but I am getting a big sound.
Okay. Okay. So can you start?
Just a minute.
Okay. Okay. Thank you. Thank you.
Mute பண்ணிடுமா
Hello?
What has happened, you see?
Yes, I am starting now.
Just a minute, just a minute.
Oh, okay.
என்னப்பா என்ன ஆச்சு ஸ்டார்ட் பண்ணிடுறாரு எனக்கு இந்த சவுண்ட் வந்துட்டே இருக்க இப்ப நிக்க இப்ப சவுண்ட் வர பாரு ஏன் why this sound is coming? You are able to hear me?
Yes.
Then I will start the session so that right. Professor Reddy sir, you say that I'm going to be the chair, right? Correct.
Sorry to intervene, Professor Reddy. If you can log off and log on again, there are some disturbances, I think.
അവർ തുടങ്ങാൻ പറഞ്ഞില്ലല്ലോ.
Is it all right now? For me it is all right, but Madam, are you able to hear?
Yes, it is very good now, clear.
Yeah, right. Very good. Professor Reddy Garu, now it is all right. Okay. Now again the sound comes. Professor Rao, Professor Reddy, can I start?
Yes, sir.
Right. We'd like to introduce the afternoon speaker. Professor A. Krishnamurthy requires no introduction. He is at present honorary director at the Center for Research in Mathematics, CMS College, Kottayam. See, he held various important positions. He was the head of the Applied Mathematics Department in Cochin University of Science and Technology. He has came through from additional professorship to the head of the department there, and he retired in 2009. After that, he was the meritorious professor in Applied Mathematics in Cochin University, with the UGC Emeritus Professor during April 2017 to 19. And he has written more than 200 research publications. Number of PhDs successfully completed so far is 39. In this case, I like to say that Professor Krishnamurthy conducted a mega event about 3 years back at Kottayam. Calling all about 70 international speakers of Russians, Japanese, and so on. Now currently he is having 6 research scholars working under him. A Russian collaboration in important project. 3 such projects went on. Now Indo-Russian project on queuing theory is going on. 2 major projects funded by NTHM he has done, and 1 more with General Motors. Professor A. Krishnamurthy requires no introduction. He is well known in the theory of queuing, and he has done his PhD at Professor Centenary of Annamalai University. Professor Krishnamurthy.
Okay, thank you, Professor Vittal. At the outset, I thank Professor Joshua, the principal of CMS College, Kottayam, for providing me this excellent facility for the presentation. Then, of course, the web administrator, Sri Mithun, and his colleagues, Anish, and a few others. They are supporting quite a bit in this program. I should thank Professor Rajshekhar Reddy for this invitation. About 45 days ago, there was the Professor P.R.R.RAO Centenary conference webinar, in which I gave a talk on interdependent processes. But here this is I'm not introducing any sort of interdependence in this situation. Rather, I look at a single server serving customers from different queues, and these customers join at several stages of service. At the commencement of service at a particular stage, a few customers can join. And then it goes on until the last stage service is completed. A typical example I shall give, look at an elevator in hotels. Suppose I am in the 5th floor and I have to go to the top floor. I need not have to go to the ground floor to take the elevator. I can get into the elevator from the 5th floor rather than going downstairs and then getting into the lift from the ground floor. Another example is what is called the lateral entry system in academic programs. For example, if you look at engineering diploma holders, they can join the regular BTech program or bachelor's degree in engineering program at the 2nd year. So they need not have to join the 1st year. Instead, they can join the 2nd year and then proceed. Another example is, suppose I have to get into a train, for example, going from, let us say, Thiruvananthapuram to Ernakulam. I am getting into the train from Kottayam. I need not have to go to Thiruvananthapuram to get into the train. Rather, I need to get into the train from Kottayam. Unlike this, so these are all bulk service in the sense that trains carry a number of passengers. Elevator takes a number of persons from different floor and take them to the top floor or at different levels, wherever they would like to alight. Now what happens in bulk service queues? There is what is called the AB rule of bulk service. I will later on show a pictorial representation. Bulk service there is what is called a general bulk service rule, what is called the AB rule. A is less than B. These are positive integers. Now A is what is called the quorum, minimum number of customers required to start service. And this is the maximum that can be served in a batch. Maximum number of customers that can be, who can be served in a batch. So in between A and D, starting from A going up to B, any number of customers could be taken for service. But then in the bulk service, what happens is the server starts service from the very beginning, and these customers have to join for service from here. So that means that the server, when he completes a particular service, he comes back, again starts service from here. For example, a transport system. So it is moving from here to say this place. So here what happens is, suppose when the transport is back here, if there are less than A customers available at this point, the server stays idle until A customers accumulate. Once A customers accumulate, service starts. Suppose the number of customers is greater than A but less than B or even up to B, then all of them will be taken for service in the batch. Suppose it exceeds B, then only B customers, first B will be taken for service. The remaining have to wait until their turn comes. So, but then there is what is called accessible batch service in literature. Literature on bulk service queue is quite vast. Long ago, Professor M.L. Chowdhury and Professor Templeton jointly wrote a book on bulk service queues. Now, they have mainly dealt with this sort of thing, different types of bulk service. Say, for example, if A equal to 1, that means service starts with just one server. It's one customer in the system. And there is a maximum that can be served in a batch. Sometimes we can take all the customers present in the system and serve. So that is a sort of ensuring the system stability. But then in accessible, where the literature is rather much scarce, accessible batch service. Suppose a service starts with a less than B customers, but larger than A, larger than or equal to A, but less than B customers. Let us say C is the number of customers in the batch, which is less than B, but larger than or equal to A. So now what happens is we can accommodate B minus C more customers in this batch. Suppose in the meantime, a customer arrived here. In accessible batch service, so far reported in the literature, it's assumed that when a customer comes to an empty system, in the sense that when there is no customer waiting, but a service is going on, and when the number of customers in that batch is less than B, he is forced to join that ongoing service batch, irrespective of how long the service has gone. That means that he will be getting only the residual service, not the whole service. He gets only the residual service, not the whole service. But then, when I want to have service from the very beginning, if I get only the residual service, I will not be of gaining anything out of that. I want to have the full service, but I am forced to join according to the accessible batch service rule in the literature presently available. But then, suppose I want to join at a later stage only. So this is the case when I want to I want to have the service right from the beginning. Suppose I want to have service from a certain stage. So then how to define that stage? That will be a big problem. As I explained earlier, in the case of the elevator, or in the case of a train I am taking, from Tirunelveli to Ernakulam train is going, so I am boarding from Kottayam. I need not have to go to Tirunelveli to get into the train. So I wait at the Kottayam station, get into the train to go to Ernakulam. So then the stages are well defined in that such problems. In the case of trains or transport buses, or in the case of the elevator, say first floor, second floor, so on, the topmost floor, or even the ground floor, or basement also included. So if I want to get service from this stage, but then it is not a fixed time, because this duration will be random. So when it comes to that stage, then I get into service. So there is a sort of randomness involved in that. When the train comes there, I cannot just say exactly when it is coming, though there is a scheduled arrival time. And then I get this part of the service. If you want to get at the final destination on the train, I get down there. Otherwise, I can get down in some intermediate stations, wherever it stops. So this is how to address this problem. That is the one that motivated us looking into this problem. This is a joint work with one of my present doctoral students, Anu Nudan Joshua, and Professor Vishnevsky with the Trapeznikov Institute of Control Science in Moscow. So the situation is something like this. Pictorially, if I represent, I have the service starting from here. Then I am going to define different stages in between, and this is the final part of the service. So I will call this stage 1, where this is the, for example, in the case of a train or a bus, transport bus, whatever, is the terminal, is a terminal, starting point, or terminus rather, terminus. And then there are intermediate stations, stage 1, stage 2, stage 3. Stage 1 is the terminus, then starting point. So this probably could be the city station. And then we have the terminus, finally, the final terminus. The service stops there. And then when it is reached, that particular one is reached, so this is the final terminus, the passengers all get down. Now look at the tourism. Suppose there is a particular tourist spot in an island. Then from the city, people get in the boat. That boat goes through various small islands, collect passengers, and finally drop at the destination, namely the picnic spot. So then what happens? Let us have a look at it. The boat has a capacity, let us say B. The boat service starts from here with at least A passengers. There should be minimum A passengers to start service. Then it moves from this, it is exponentially distributed. Now I have just made use of the assumption exponentially distributed amount of time to reach here. This duration, which is exponentially distributed, has a parameter which depends both on the number of customers in the batch undergoing service as well as this initial state. So it is mu1 superscript some number, which is the number of customers in the batch. So call it B1. Then when it comes here, more passengers join, provided there are somebody waiting. So they can join, provided it does not exceed, total does not exceed B. So number that can join here is B minus B1. At most B minus B1 can join from here. Suppose B1 are waiting, B1 passengers are waiting, and this is our excess capacity available or vacant seats available. Now the minimum of these two is the number of passengers who can be accommodated from here. And again, it continues. So here, moving from 2 to 3, it takes an exponentially distributed amount of time with parameter mu sub 2, which depends upon the stage 2, and we have a superscript here. I call it B2, which is larger than or equal to B1, which is the number of passengers that is in the boat, starting from, who are in the boat, starting from stage 2. Now having come to 3, again passengers can be accommodated according to this rule, and until finally it comes to this terminus, the picnic spot. So now why I assumed the exponentially distributed service time? That is an advantage, because then I did not have to go for supplementary variable technique for the analysis, because the arrival process at station 1 I have made a very weak assumption, weak in the sense that it's a very general, pretty general arrival process, which is map. So it is a map I'll just define. So customers arrive to the first terminal according to the Markovian arrival process. Is what is called Markovian arrival process. They wait there for their turn, and subject to maximum B customers, each batch service will start. Then starting from this stages onwards, there are fixed finite capacity waiting stations. This waiting station has infinite capacity, whereas the intermediate stations, 2, 3, so on up to k, they have only finite waiting capacity stations. So C2, C4, etc., Ck are the waiting room capacities which are finite. So the process continues like this. The question naturally that will be arising is why boson, because assumption of arrival process starts from 2 to k, stages 2 to k are boson processes. So for example, at the stage J, customers arrive according to boson process of rate lambda J. J equal to 2, so on k. Whereas in the first one, stage 1, customers arrive according to Markovian arrival process. Of course, I could have thought about having a marked Markovian arrival process instead of a Markovian arrival process, marked Markovian arrival process. What's the advantage? Well, I can just group them. So, first of all, I will define what is a map or Markovian arrival process. What we have is a Markov chain on a finite state space. Let's call the state space or the Markov chain or label it as consisting of m elements 1 to m. I label them as consisting of the states 1, up to going up to m. Well, they are all communicating. So it is a reducible Markov chain that I am considering. In fact, it is an extension of what is called the phase step distribution. In phase step distribution, I have an absorbing state, at least one absorbing state. Here, no, there is no need of a specific absorbing state. Now I am going to consider transitions among these. Because it is a Markov chain, so I have to have an initial probability vector. So the initial probability vector is designated as alpha bar, which is equal to alpha 1, so on alpha m. That means it can start service initially at time 0. Thereafter, this will not have any role. That's the interesting thing. Unlike phase step distribution, this initial probability vector will not have any role once the first service starts. So it can start in state state 1 with the probability alpha 1, so on state m with probability alpha m. And the sum of these alpha 1 to alpha m, that will be equal to 1. So a Markov chain is now completely specified if we are given the initial probability vector and the one-step transition probabilities, or I will call it one-step transition probability matrix. So Pij, I and j varying from 1 to m. Now these two define a Markov chain completely. So it is uniquely determining the Markov chain. Now having done that, now let us look at two matrices, D0 having entries D sub ij with a superscript 0, and another matrix D1 Dij with a superscript 1. I will tell you later what exactly is this 0 and 1 are standing for. Now I assume that transitions among the states in the Markov chain are according to an exponentially. So suppose the process is in state I at time t, then in the next interval of duration, a very small duration, say t plus h, it can move to another state j with the probability dij. Now this will be with an arrival with the probability the rate, I will call it a rate dij1, and it will be without an arrival with the rate dij0. So this is rate of the exponential distribution or the parameter of the rate of moving from I to j in Tt plus x. So dij is 0 and then dij 1. That is with an arrival. 1 stands for an arrival and 0 stands for a transition without an arrival. And then it again stays there for an exponentially distributed amount of time with, I did not stress on that. Now that will depend upon the state in which it is in. Suppose now it has now come to state j. Now it is going to stay here for an exponentially distributed amount of time with parameter that depends upon the state in which it is in and the state to be visited next. Let us call it some L. So this is like, therefore, a semi-Markov process. In fact, a semi-Markov process is much more general because in a semi-Markov process, sojourn time need not be exponentially distributed. It depends upon the state in which it is in and the state to be visited next. But the distribution need not be exponential. It can be an arbitrary distribution. For example, I can have a density Gij, or I can use something like this, or capital Gij, either. So there is no problem in looking at that. But then I will not be able to have a continuous time Markov chain out of that. And therefore, I chose to look at the sojourn time as exponentially distributed. So it is exponential distribution being a particular case of the class of distributions having the lag memory property, and therefore I need not have to bother about what has happened prior to time, the present time, in order to determine what is going to happen in the future, probabilistic determination of that. So this would mean that I have a continuous time Markov chain where the transitions in the arrival process will be according to semi-Markov process. It's according to a semi-Markov process. With the sojourn time in each state depending on the state in which it is in and the state to be visited next. The state to be visited next is determined by this transition probability matrix. So once in a particular state, it reaches a particular state, it decides the state to be visited next, and then only the sojourn time comes into play. So this is a particular case of a semi-Markov process. Phase time distribution is similarly defined, but only thing is there is an absorbing state. Now the advantage with this map is that since there is no specific absorbing state here, so suppose it happens that an arrival takes place with a transition from I to j, then j is going to be the starting stage or phase of the next arrival. And then until that arrival takes place, suppose the arrival takes place when a transition takes place from a state to say k to state k dash. So k dash is going to be the initial state for the next arrival. So it goes on in that fashion. So the Markovian arrival process is therefore completely defined, and therefore the matrix D naught is of dimension m plus m and having entries dij 0, that means without transition, without an arrival. And D1 has rates of transition from state I to state j with an arrival, coupled with an arrival. So this pair, D I call it and write is D equal to D naught D1. This describes the Markovian arrival process completely. That particular Markovian arrival process completely. So having done that, I can define now what is called the Markovian arrival process. Suppose I want to consider different types of arrivals, not just one type, different types. For example, different priorities. Suppose there are k different types of priority customers arriving. So typical example is the problem that we are discussing here, that customers will be arriving to various stages. So there is one type of customer coming to customers arriving to stage 1. Another set of customers coming arriving to stage 2, and so on. Yet another section of customers arriving at CK. Now, how I can just take them all together? I can, instead of going for post-on-arrival processes starting from stages 2 to K, I can very well include them in a Markov-in arrival process. So just like saying that the arrival is of type 1 with the probability P1. So in general, type J with the probability Pj. So we have K types of arrivals. And accordingly, we can define the matrices D0, D1, so on, Dk. So D1 will be taking care of, no, D0 takes care of the fact that transition among the states of the Markov chain. So basically there is a Markov chain as I have defined earlier. Transitions take place according to the semi-Markov process, but then sojourn times are exponentially distributed. D0 stands for transitions that take place without an arrival. Then so on, Dj, for example, the J plus 1 entry in this one, Dj, that has customers of the type J. So Dj will be essentially Dij. Now I'll write J here just to, oh sorry, I'll use a different notation. Here I'll write J, but instead of J here, I'll write here DIL, DILJ. So Jth type, so this means that we need just to have a representation like this for the whole arrival process. Otherwise, if you assume that customers arrive to different nodes according to Markov-in arrival process, then for the first node we have to consider D0, D1. Second node, yet another one. I have to say, just write say D0, a superscript or something like that. I have to write. I'll have a something of this sort. That means to the first node. Then this is a first node with an arrival. The other one is second node without an arrival. Then this stands for with an arrival, and so on. But then this complicates the issue in terms of dimension. So I will have a large number. So instead of having this 1 D0, 2 D0, so on, K D0, all these can be clubbed together in this D0, and thereafter D1, D2, so on, D2, Dk. That will take care of arrivals of the distinct types. So Markov arrival process will be in fact extending the result that I am describing here. But the difficulty is that dimension of course will be increasing because I have to keep track of the phases. Whereas with the post-on arrival process, I need not have to bother about the phase of the arrival process because after all there is only one transient state. And once an arrival takes place, the next arrival starts. There is no problem at all. That's the advantage with the post-on arrival process. So having given the motivation for the problem, now I go to the mathematical plane of the problem. So this is a typical figure that we have. Now for the mathematical formulation, what I do is, I have to analyze a continuous chain Markov chain because of our assumption we can have a continuous chain Markov chain. So first one is the number of customers waiting in the first stage. Then N2T, number waiting in the second stage, and so on, NKT, number waiting at the kth stage. Now thereafter it is absorption. Now, along with that, we need some more information. What are those information? One is concerning the state in which, or the stage in which the service is going on. For example, it may be at the stage I. It is moving from I to I plus 1. Remember, this is actually much less than the movement in a phase tape distribution, in movement in or map, where the arrivals need not be in the forward direction alone. It can be in backward direction as well. But here, in a transport system, of course, we assume that the process moves forward progressively. So ST is the phase or stage at time t where the service is going on. Then I have an I of t, where I of t stands for the number of customers in a batch, undergoing service, number of customers in the batch undergoing service. And then additionally we have, because we have something which does not as such possess the Markovian property, namely the Markovian or Markovian arrival process. So I have to prescribe the state of the arrival process. So state of the arrival process, state of arrival process or stage of arrival process. So these are the requirements. So I have therefore a Markov chain N1T, N2T, so on, NKT, S of T, J of T is that what I have used as the number of customers undergoing service. Perhaps no, it is just interchanged. Anyway, there is no problem. And then the one is taken as I of T. Anyway, it is not going to create any problem. I did not look at this while writing this. And therefore, now S of T, the service batch size, the stage of service, the JT is the service batch size, and I of T is the phase of the arrival process. Now these things constitute, therefore with this information, I have a continuous time Markov chain. So these are the things required to get a continuous time Markov chain. Having got a continuous time Markov chain, now the problem is to analyze that. So naturally we had to write the differentiation, but that is rather a very complicated issue because it is a complicated structure that we have here, relatively complicated, but if I go for Markov process, it is going to be still more complicated. So what I am going to write is, give a typical example for a, look at this one, the infinitesimal generator, that means what is happening in a short interval of duration dt plus h or t plus dt. This is what we are going to look at. Now, in this infinitesimal generator, what I have taken is the A, the quorum is taken as equal to 2. There should be at least 2 customers present at the initial node to start service. And the maximum that can be served in a batch is taken as 4. So that is the next one, P equal to 4. So with that, what we have is the infinitesimal generator matrix Q1 equal to B naught naught, B naught 1. Now the extreme northwest corner, this is standing for transitions within the phase. For example, N1T is taken, this is equal to 0. That is the 0 standing for. The other one stands for the rest of the things, transitions. So 0, 0 would mean that it takes care of the situation where there is no customer in the system in the phase, in the stage 1. The arrival process is going on. Description of the arrival process, So there is no customer batch in service, and therefore no stage is required. What we require is only information. The N1T is 0, N2T, so on, NKT. This can be different from 0 because only if there is somebody initially available, the service starts. And then, of course, you should know the last one, namely the state of the arrival process. So I have just crushed the dimension into, well, this was 0, this is equal to 0, this can be anything between 0 and its capacity, and so on, up to the maximum capacity. And then phase of the arrival process, which can be anything from 1 to m. So with this one, that is a 0, level 0. So this is transitions within that phases. So these are all referred to as sub-levels or phases. Now suppose an arrival takes place. That is what is indicated by B01, the next matrix. That means the one on its right side, B01. To a system with no customer at the initial node, at node 1, one customer arrives, which means it is the D1 matrix that will be coming to play. And then therefore phase changes will be taking place. So that will be taken, that is taken care of by that. And then B10, B10, the second row, B10 stands for the situation where there was only one customer, there is only one customer waiting, and it goes to the level 0. But that as it is not possible. No, sorry, it's okay. There's no problem. 0 would mean that there is one customer waiting initially, service is going on, but then the service is getting completed without any further customer available. So it just stays there at this one. Then B20, B30, B40, all those things are available. Then if you just look at these things, B1, B2, etc., we get a repeated structure from level, say for example 5, they are shifted to the right, there is a B51. That means that a service is completed, now there are 5 customers waiting, and then it just drops down to 1, because maximum 4 customers can be taken in a batch. So now it is going to 1. In fact, I should not have considered this B10, B20, B3, all those things should have been. B10 should be, there should be 0. It is considering only, looking at only what is going on within. It should not have been represented at B10. Then B20, yes, that is possible because with the service completion, 2 customers waiting, they are taken for service, and then there is non-waiting because both of them are taken for service. So there is nobody waiting in the first station. That is why it is labeled as a B20, B30, up to B40, it is taken care of. Then there is a shift to the right, B51, which means that maximum 4 customers can be taken for service in a batch, and therefore 5 minus 4, which is 1. Therefore, it is number waiting is reduced to 1. Of the 5, 4 are taken in the batch for service. So no further customer can join for service from other stations. That's the meaning of it. So the process continues in this fashion. Now what happens is, if you look at the previous one, it has the structure of the MG1 type. Now instead, suppose I take B A equal to either 1 or even 0. When the service is completed, has come to the terminus, last one, the server comes back and starts service from here. He starts service, suppose I write A equal to 0, which means that even without a customer waiting, the service starts. So there is none to be served in that batch, that's all, initially. So it comes to 2, takes passengers available according to the rule. If you take A equal to 1, again same process can be getting repeated. So what happens is, we will get a structure of this type. So it is essentially an MG1 type structure that we get. But then we are going to do something much simpler, not mathematically tractable. We need not have to bother about all these things. We are going to rescale with the modulo A I am going to just to take, and therefore I am going to redefine. So in this process, B0 denote transition rate matrix from n to n plus 1, B1 denote transition rate within level n, and B2 transition rate matrix from n to n minus b for n greater than or equal to a plus b. So then B2 is I Kronecker product this. All those things we will be getting. It is rather simple to see. The transitions rates are indicated in this one. And then level 0 to level 1, how it is happening, all those things are given here. I will just skip these things, but then I am going to just look at the situation. The previous slide will be telling something about what we are going to just rescaling by A, which means that I am going to redefine levels as multiples. For example, in a level, so 0th level, the following elements are available: no customer, one customer, so on, A minus 1. So this is our level 0. So these are sub-levels in the level 0. Then next is level 1. Level 1 would mean that we have A up to A plus 2A minus 1 customers. So that is level 2. Level 2 therefore would mean that, level 1 would mean that there will be A plus 1 or up to 2A minus 1 customers. That means there will be A elements in each level. So we rescale or redefine the levels, and that way we can reduce the computational complexity to some extent. So, but then one could have also done for a, so this will not give rise to a level independent QBD structure. If you want to have a QBD structure, which means that a tridiagonal structure for the Markov chain, infinitesimal generator of the Markov chain, we can redefine the level in terms of B, the maximum batch size. That means that level 0 will be then defined as consisting of the elements. 0 level would mean 0, 1 going up to B minus 1. Then level 1 will be started from B up to B minus 1 and so on. So that is the redefining of the level. It will produce a level independent quasi-Berthoudet process. But then we go for redefining the level in terms of A. We still get the MG1 type Q, but then there are some advantages in the computational process. And this leads to the stability condition. Now with the A as the rescaling of the level, and then we get this structure that is indicated the previous thing, but then these things, there will be some modifications. Anyway, so what we are going to get is the stability condition. Define phi is equal to phi 1, phi 2, so on, phi A. So just to see why that A comes is because of that. Denote the state space of the steady state probability vector of the generator matrix C equal to sigma Ci, because there will be this many elements to the left of the main diagonal, and therefore define C as equal to sigma I equal to 0 to S Ci, then phi satisfies the equation phi C equal to 0 and phi E equal to 1, total probability equal to 1. So phi C equal to 0. So this is the probability vector. That means within the when the system stabilizes and we have a repeating structure, that is what is actually seen in this slide. If we look at this slide, we can just see that a repeating structure from certain level onwards. So with that, we get this thing, phi C equal to 0, phi E equal to 1, C is a block circulant. The advantage with this C is that it's block circulant, and therefore that means that the blocks when just moved, permuted, that will be actually giving us the steady state probability vector of the finite system, that within that level it is given by phi equal to 1 by A, E prime A, Kronecker, phi tilde, where phi tilde satisfies phi tilde sigma j equal to 0 to 2 bi equal to 0. So it is just connecting so many things. That's how we just get this relation. So K is stable if and only if this is satisfied, which means that we have a simplified system. We get the stability condition. So this left hand side reduces to lambda 1. Lambda 1 is the arrival, fundamental arrival rate of the Markovian arrival process. So that is lambda 1, and therefore that is less than the service rate. That is what is indicated by the stability condition. So we get this is stability condition, and then for the stability vector, system state probability vector, we have the equations x q2 equal to 0, x e equal to 1, and then all those things computed. So we get these systems of equations, and then that matrix R, which is a rate matrix, that can be easily computed in the present situation because that's circulant property. So we get this as the C0 value, and then because C0 is this structure in the repeating structure, that matrix, block matrix C0 is this structure. So the rate matrix R will be having entries, block entries, all zeros up to the m-1 row, and the mth row it will be equal to R1, R2 non-zero entries, non-zero block entries. In fact, they are all non-negative. They are not essentially zero, they are non-negative, and at least one element in each block matrix will be positive. So the expected idle time we get, the expressions are given there. Now, there are so many things computed. For example, distribution of service time. Suppose the customer joins from stage J in between 1 and K, and then how long he has to wait is indicated by this. So the transition rates are indicated there, and then this is essentially the absorbing state. And time until absorption in that is computed. And you get for that a phase tape distribution. The expected queue length and all those performance characteristics are computed thereafter. And then probability server serves a batch of size M. So that you can see that the service batch size we have an M there, and therefore that is the last but 2 coordinates. M is seen there. Okay, so this is just getting completed. Now there are some computations given along of order 2. That means we have 2 stages. ZAC stands for zero correlation. So we have a matrix D0, D1. That means the Markovian array process D0, D1, the pairs are defined there. The Markovian array process with the positive correlation, we have 2 matrices D0, D1. And for a Markovian array process with the negative correlation, we have the 2 matrices D0, D1. and the correlations are also indicated, and then a number of computations are made with the service rate MUGM for various size. So I'm just completing it. So there are a large number of references that one can see. So I'm just concluding with that. So the advantage with this is that it takes care of the customer's need rather than ask him to join and a service batch which is already in service for a certain amount of time at the time of his arrival. So this has a lot of advantage over the existing work in the queuing theory literature. All right, thank you very much.
Very good. Thank you very much, Professor Krishnamurthy. He has done very nicely, starting with the later entry to a queuing system, going from a Markovian to non-Markovian process, making the transition continuous, and then arriving at the continuous drive transition problem. We thank Professor Krishnamurthy for his excellent presentation. If any question, probably they can contact him. As the time is over, we now start the next session.
Okay, thank you very much, Professor Vittal.
Thank you. Some sound is coming. Can we go to the next talk? Now, I'd like to introduce Professor Arivaringan. Professor Arivaringan is a retired professor of statistics from Madurai Kamaraj University. He was the UGC Professor Emeritus Department of Statistics, Madurai Sundarnar University, CSCR Emeritus Scientist, School of Mathematics, Madurai Kamaraj University, Chairperson, School of Mathematics, Madurai Kamaraj University, Head Department of Applied Mathematics and Statistics, Madurai Kamaraj University, Coordinate Curriculum Development, Cell, Madurai Kamaraj University. He is a Fellow of Royal Statistical Society UK, Fellow of Academy of Sciences, Chennai. He is having teaching from undergrad to postgraduate and DSc courses. His professional experience started from a lecturer in Government College and he entered into a senior most professor here to Madurai Kamaraj University. Professor Arivaringan, for 16 PhD student in international journals, he published 96 papers and very prestigious journals, and he has undertook 6 projects and 12 minor projects, technical reports 9, 1 proceeding, and lot of lecturer materials in the Madurai Kamaraj IRFI University. He has taught for MSc Computer Science and MBE. His field of research, stochastic modeling and inventory, probability and statistics optimization technique, conducted many hands-on training on SPSS work. With membership in professional bodies, life member in International Indian Association of Statistics, Indian Bayesian School Society, Indian Association of Production, Quality and Reliability, Indian Society of Medical Sciences, Operations Society of India is a member. He is an advisory to the UPSC from 1997 till date, consultant to Cellular Software and many more institutions. And Arivaringan is well known for his teaching as well as a research ability, and a good team in Madurai. Even after retirement, is pursuing active. Professor Arivaringan.
Good afternoon to everybody. I am very thankful to Professor Vittal for giving me some nice words about me. Sir, am I audible to you, sir?
Yes, very much.
Okay, sir. I also thank Professor Rajeshwar Reddy for inviting me and allowing me to participate in this great event. Now, I will present my entire screen. Yes. Professor, are you able to see my screen?
Yes, 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 we are able to.
Thank you, sir. Because we are working in remote. I
Yes,
don't know
yes.
whether I am audible or I am visible. Okay. My topic is a discrete time production inventory system at service facility. It is co-authored by my colleague Sophia Lawrence. Once she was my scholar. Currently, she is in Madurai Kamaraj University, and I am at MS University as an emeritus fellow. This is a table of contents. Well, this seminar has a wide range of topics. So I would like to point out where I do stand. The subject is stochastic modeling. The sub area is modeling of random inventory systems. Under discrete review, I will explain these terms. I am going to use the tools discrete phase type and DMAP. Just now, Professor A. Krishnamurthy has done some aspect of Markov arrival process, but I am going to talk about the same MEP, but in discrete time point of view. Well, I am interested in studying inventory systems. I will say some earlier milestones. This EOQ, sorry, it was a mistake, economic order quantity formula was first developed by Harris in 1913. But in industry, people are using this and they call it as a square root formula. It goes like this: square root of 2 times demand rate and setup cost divided by holding cost. But first mathematical proof was given by Harris. The next, in 1958, R.O. Carlin Scott, they provided a similar work as that actually changed the research work in inventory by adapting the stochastic methods. After that, last half of the quarter of the 20th century saw a great development in this area. Well, in inventory systems or the inventory control, there are two major decisions we will take. You know that the inventory is having some stock, a physical stock. If the physical stock is become very low or small, you want to replenish. That is, you have to make an order. So, how much you have to order, how much at what time you have to order, that is the important decisions. If everything is deterministic, then there's no problem. You can compute the time and the quantity. But everything is in random phenomena, that is, everything is affected by random quantity. In that case, the decision to make when to order and how much to order is becoming complicated. So we need stochastic methods. Now, before I go into model, I want to point out that inventory is reviewed initially the last 20 years of 20th century. People consider periodically at specific time points. In industry, you can look at every day morning what is the stock, or every week beginning, or every month beginning. So the specified time points usually it's equally spaced, and most of the earlier research are considered this. Then came this method. It is actually, this is a continuous time. Whenever there is a demand or replenishment or any other event, the manager of the inventory wants to attend immediately. Because some years back, you place an order, you wait for it. The order is received, but it is not taken to your stock. So there is a time lag. But with the current technology, immediately whenever the stock is received, they can immediately take it and put in the shelf. Whenever there is a demand, they can immediately expand the item. So I should say that periodically reviewing the points and see the various events. I should say various events, demand times, real times, and the time of receipt, etc. So these are first method people used the last quarter. Then came the continuous review or continuous time axis. They review at every point as and when it happens. Now, in this 21st century, people are considering the time axis divided to small time slots. So I should write like this. It's not first week, second week, third week, but every day or every hour or every 10 minutes and so on. It's a small piece, but it's a small time slots. This actually impact from the computing field. The servers are looking at each customer or each logged user at specific small time slot. If there is a request, it will attempt. It considers. Otherwise, it go to another one. So there are time slots. The digitally enabled systems look only in a small time slot. They are not continuously watching it. Particularly, the idea is just from telecommunications and digitally monitored systems. So my research area, I want to just give an idea, at least to the extent to which this current presentation matters. Inventory system is reviewed at discrete time slots. This is not a month or week, maybe a small 5 minutes or 1 minute and so on. It's a small one. Customer demands single item. Bulk demands are not allowed here. That will be given to or released to the customer after performing service. So you can think of this way. It's a combination of queue and inventory. Inventory items are stored, released, and in a queuing model, every customer is served. So here I am combining these two. So how we are going to replenish the stock? There are two modes: made to stock, order to stock. This is the usual practice. Every factory, assembly units, they order the items from external stores, they keep it. So order to stock. Sometimes people like to manufacture and keep it ready in their assembly line. So why we did this? I will give some examples. So in my model, I am going to consider there is a production item. I am not going to use the order to stock, but made to stock. The reason I will tell in the next slide. Production is started when the stock is very low. Please note that it is not always on the production in the running stage. We are going to start the production only when the stock is very low, and it reaches some full or some prefixed capacity. We are going to stop. So the machine will be producing items only during certain period. This I need it. Okay, then we are going to consider the arrival process or other distribution service times and the production times and so on in a very general setup, like as Professor A.K. told Mark arrival process, but I am going to present in a discrete time. So the necessity of production. So I told you, procure items from outside or produce in factory as and when needed. So the first one is has a lot of literature. The second one, only recently, only in the 21st century, people started looking at the problem, and most important results are coming only in this last 20 years. So why this is necessary? Why the production is necessary? To cope up with the changing technologies. See, in cell phone industry, the technology is going on changing. Even not a year, even within a month, the technology changes. You need the latest quality. Therefore, the changing technologies force the company to produce in service, in home. They can't place an order and wait for receiving it and so on. Many times, to be the specification of the products need some fine tuning at the time of assembly. So it's necessary that they should produce. In some cases, the trademark rights must be safeguarded. You can't give to others. But certain time it is not avoidable, but certain industries, they want to safeguard the rights. Most important is to protect production secrets. And one particular problem, I was using a washing machine. I needed some particular powder. I want to buy from the company at a high rate. Later only I know that is nothing but a colored salt. So one mechanic told me use the colored salt or give without color. So sometimes the industry wants to keep their secrets. So again, I don't, these assumptions I already told. Now let me go to the your physical realization. So this area, inventory stock, it can go up to capital S, it may go to zero. The next one is the waiting hall. When the customers arrive, when they ask for the item, when it is being prepared, he has to wait. Or if more people are there, they have to wait in a hall. So at this point, a demand comes. That means the customer arrives. So here you can see that this goes to 1. It stays there for some time. And actually, at the time of receipt of the demand, service started. When service is completed, the inventory level goes down because that item is serviced and it is given to the customer, he goes away. In that case, the customer leaves the system. So, in this graph, this graph depicts the customer level. Initially 1, when he leaves, it goes 0. Again, when the next customer arrives, the number 1 is increased in the hall, in the waiting hall, and suppose this is the service time. Only after the completion, this will drop. That is, the item will be issued, so inventory goes down, the customer leaves. So this can be happen in any ways. But what we are doing is, when the inventory hits at a level, I am going to fix as a small s to distinguish between capital S, that is the maximum capacity. This is prefixed, not prefixed. Actually, I will take it as a additional variable. I have in my model, I have to find out this. Okay, when it hits the small s, a production started. So demand comes and service is going on. When service completes, the customer leaves, the item is removed. In case there is no item, that is, the inventory drops to 0. That means all the S items are utilized. After that, when customers are coming, they will not be able to get this as their product, but they have to join the hall, waiting hall. So this is my simple view of a problem. Now I am going to talk about the discrete time phase step distribution and discrete time MAP. Please note that just before my talk was AK gave a map but in continuous review case, but I am going to talk about in discrete case. So to fix your ideas, please note that time axis is divided into many slots. In periodic review models, this length will be very large, but in digitally enabled services, they are very small, maybe 5 minutes or 1 minute or 10 seconds and so on. So what will that happens in between here or here or here, we need certain assumptions where to record it. It may happen here or it may happen here or here. So what we are going to do is certain assumption, not for the practical side, but for the theoretical side. Okay. Now, when I present my model, I will explain these things. Now I am going to consider a class of phase step distribution, I simply call PH, a class of Markovian arrival process, I am going to call as a MAP. Now, why should I consider PH and a map? This helps us to get a flexibility. The flexibility comes in this at the element level. If you think of this is x, so x has a exponential distribution. This is the useful assumption being made for a long time. In the continuous case, but in the discrete case, this will be a Bernoulli process. Sorry. Okay. X will have a Bernoulli process. I'll explain. So, what is the problem here is the mean and variance are related in a simple way. But if you consider a case where you want to find the data and find the mean and variance, they may be very far, they may be very different. Of course, mean and variance will be different. For Bernoulli process, mean is P, variance is P into 1 minus P, but they are related. But when the actual data has got a wide range of variation, this model, this assumption of Bernoulli process gives trouble. Now look at this way. And I would define a distribution is in PH, a class of distribution. If the distribution is the time until absorption in a finite state Markov process. I think I should give some another example, easy to say. I'll jump to another case. Yeah. Consider a Bernoulli distribution. We define that mass function as 1 minus p if x is 0, p if x is 1. This is called a discrete time, discrete state space Markov chain, and actually is a sequence of arrivals at each time. It's a Bernoulli distribution. Now we look at this diagram. At this time, Bernoulli process results in value 1. Here, the Bernoulli process results in 1. Here, 0. I am going to assume whenever there is 1 arrival, whenever there is 0, no arrival. So this typical relation depicts the arrivals at time slots, but if you look at the time between any two events, it's a Bernoulli. That is, I mean, it's not time, it's a jump from here to here, here to here. This happens with the probability mass function, that is Bernoulli. Another way to look at it, look at this way. You have Markov chain with the two states 1 0 1 0. The TPM I am writing here, the first row P to 1 minus P. There is from 1 to 1, the probability is P. From 1 to 0, the probability 1 minus P. Once you reach 0, the probability to go from 0 to 1 is not possible because jump back to 1, jump back to 1. Whenever you jump back to 0, you are going to stay there. So, this is the discrete time absorbing Markov chain. So, what I do is, at time 0, I look at this. It jumps back to 1, like this. So, no arrival. Again, it jumps back to 1, arrival, no arrival. But when it jumps back to 0, like this, then I assume there is a absorption, or I synchronize my absorption time to an arrival. So this length is a random variable, but we all know from simple mathematical statistics, there are many failures, finally one success. There is nothing but a geometric distribution. So from Bernoulli process, we repeat it again and again, particularly when you consider absorbing Markov chain, and whenever an absorption occurs, you assume there is arrival, and again you restart it. Restart that. That's important. I just want to again, in Markov chain theory, we have additional vector, that is the initial probability vector. When I say alpha equal to 1 0, the probability 1 for state 1, probability 0 for state 0. That means I start at 1, I can't start at 0. If I start at 0, that is this is the probability, this is the state. If I start at 0, I will be there only. So my probability will be here only, that is avoiding 0. When I specify this, I have starting my Markov chain at state 1, that is here, and I may be having many jumps back to it, but when I jump to 0 like this, I am going to assume an arrival has come. That is, I am synchronizing my arrival with the absorption. But after that, I have to start again at 1. So this initial probability vector assures me that I will start again at 1. So this way I can go on repeating it. This is yeah. This as an extension. Okay. Now go back to our yeah. So I told you about two-state observed function. This can be extended. The idea is, think of M as a vector of 1, 2, 3 up to M. So this will be M plus 1 by M plus 1 absorbing Markov chains transition product matrix. Again, my initial product will be 0 for last row, some alpha for the remaining. So when I have only two-state space of Markov chain, observed Markov chain, I got geometric distribution. Now so I'm going to have a jump from 1 to or if you call anything 1 to 2, then 2 to 3 and so on. When it reaches this one, because it can't reach to 0, all properties are 0 here, only when I have MSP here, from this state only I can come here. So in other words, I'll be jumping within state 1 to M using these properties. Please note that I'm going to have I'm going zeros, but it can be extended. I should have positive values and the other positive or non-negative values. So I can simply extend this. Now, before I go to the map, I think I should give done 41. See. Yeah. Now, if you look at this, a matrix, another a column vector. So this gives me the transition properties for moving from any one of the M states to any one of the other M states. So when I am just jumping, or when I have this probability for moving from any one of the state from M to another state, I will be simply just going to various states, but this probability gives me I am going to 0. Then I got absorption. So this I am going to extend. This I am going to replace by another matrix. This is a T, another matrix. This I am going to do it here. A matrix. So these are the probabilities going from 1 to 1, 1 to 2. Here also 1 to 1, 1 to 2. Please note that Professor Krishnamurthy said this is something constant property that gives no arrivals. Here, a transient property that goes with the arrivals. So this idea is heavily used in continuous time MAP, but in discrete time map, that is, I am going to have Markov chain. In Professor AK's thing, the diagrams are negatives, at least for D0. But this is a Markov chain, not a Markov process. Therefore, this will be always, this both will be non-negative. The row sums of whole matrices is 1. So I will come back to that is my map. So in D map, arrivals are governed by underlying M state Markov chain. There are two vectors D0ij, D1ij. I and j vary between 1 and M, but when I indicate that by suffix 0, suffix 1, this is a transition from I to j, but there is no arrival in the my process. When I indicate 1, there is another set of probabilities. They are associated with the arrivals. So I go to define matrix D0 and D1, and when I make a sum of these, the row sum will be 1. In other words, the row sum is a stochastic matrix. Now the important point or important trick is this sum, the D will have a major row, and I am going to have an invariant vector or stationary vector for D. Using that, indices can be derived. Particularly when I say there is arrival rate, that is usually everybody asks if there is a Poisson or exponential, the parameter gives the arrival rate. So here the arrival rate is given by the pi, the invariant vector of this D matrix, and the sum and unit vector, all ones. So this gives you a single value, because this is pi is a row vector, this is a matrix, then it's a column vector. So you are going to get a single value, that is the rate. And there is a vast literature available on map and D map. The major source of information is Ian Newts and Latochi and Luke Anthony and others. You can just Google it, you can get very interesting papers or results. Well, let us come to my problem, my model. The arrivals, when I say arrival, a demand comes, or a person comes and asks for an item. So arrivals or demands are used interchangeably. These follow map, that is D0, D1. D0, D1 are giving various transition probabilities. By using different values, you can consider different combinations. One advantage is, unlike other renewal process, the arrivals here are correlated. A correlated arrivals is possible here. Most of the Markov chain renewal process, Markov process techniques, we need at least one time, or this is conditionally independent assumptions, and in renewal process we need a completely independent process. But by choosing D0 and D1 correctly, suitably, I can have correlated arrivals. So this is a more general case than the usual renewal process technique, not Poisson process. So arrivals follow the map. I am going to have a D0 and D1, and please note that when the arrival occurs, according to probability of D1, then that state is the initial state for the next initiation. So arrivals follow D map. The service time usually we take exponential, and we have done many problems with that assumptions. Now we are going to have a base type. This is called as initial probability vector. That is to start. Once observation is made, you have to start at some point. So alpha T is the transition probabilities within the non-absorbing state. The production is switched on when the inventory level is dropping down to a prefixed level small s, but that for my problem that can be taken as a addition variable. We are going to find out. And the machine is switched off when the inventory level goes to maximum. That is, the full capacity is received. Even if you produce, you can't keep it anywhere. So when the inventory reaches the full capacity, you stop. The production time has a discrete PHD distribution. It is the initial probability vector. This is the probability matrix for the transition among non-absorbing states. Here N1 is the number of states, number of phases, N2 is the number of phases here. Please note that I got the arrivals, that is map, service time as well as production time. Both are phase time. So by having this, if I need, I can boil down to exponential distribution by using very simple matrix. But here, I'm sorry, I'm going to do the discrete case. So by choosing B equal to 1, 0, this observing Markov chain, this becomes geometric. So whenever I need a special case, I can come down. Moreover, very general distribution can be framed using phase take and map. So I have done various cases, various examples, but my presentation will be only up to time, I think 4. Okay, I'll just rush through. The customer does not join and leave the system if waiting hall reaches capacity. That is the finite waiting hall. So arrival and production occurs in the slot N. It is deemed to occur at lower boundary. This I have to say 3, 4 means it will occur at 3. The service companies occurs at the upper end. So this is some assumption I make because I won't write the probability matrices. In practice, people use in any way, but when I go for mathematical modeling, I need certain restrictions. So what I did, I modeled the problem by suitable stochastic methods. Here I am using a Markov chain approach. I have obtained the long run probability distribution of the joint inventory level, machine status, number of customers in the waiting hall, and so on. These three variables taken as a joint, a vector. For that, I consider, I find, or I should say, I indicate how to get the log probability distribution. I derived the distribution of PC period. I am not going to show here for what of time. I obtained the distribution of production cycle length, and of course both in steady state. In constant state, it's very difficult to get, so we are concentrating upon steady state. The period is just and distribute the waiting time. These three items I am not going to present here. This will not allow my, I do not have much time to do it. I have calculated the measures of system performance. That is, what is the inventory, average inventory level, what is the average number of customers, and so on. With that, I am going to find a total cost per unit time. For that, I have to find some cost structure. Okay. Some literature here. Do is, Professor Krishnamurthy has also done some work in discrete time and particular inventory. Here, for my knowledge, there are two papers. My student and my colleagues had done some work on discrete time inventory. Well, now at any time, any time slot. Excuse me. At any time, I would use this as a random variable at time t. There is the inventory level. This is number of customers. The state space is 0 to capital S. The number of customers in the hall. The state space is 0 to n. ZT, status of machine, 0 means off, 1 means on. J1 of t, J2 of t, J3 of t are the indicators about the phase. Please remember that there is a transition among a Markov chain. At particular time, it may be in state 1 or 2 or 3. So that state is taken as a phase. I am going to indicate this actually is a way to capture the status so that I can have a Markov chain. This J2T indicates the phase of the production process. Production process goes to from 1 to N1. Then at any time, I'm going to just capture. Please know that with that, I have the power to model. I don't need in a supplementary variable technique. J3T is the process, the phase of the service process. So I got a vector 1, 2, 3, 4, 5, 6, 6 vector. A vector process. The T takes only 0, 1, 2, and so on. Now I know that LF takes only value here. Z of takes value 0 or 1. N of t takes value 0 to S. Now I consider vector process. We should not think that this is just a cross product. The state space of this process is not the cross product because the values taken by these variables are somewhat interdependent. So I am going to make a list here. Inventory level 0, 1, 2. I have got some listing here. Machine status 1. Here 0. Please note that in this region, when the inventory is small s to s plus 1 to capital S minus 1, the inventory may be on or off. For instance, if it is going up, inventory is on. I mean, machine is on. When it reaches the capital S, machine is switched off. So when the inventory is yes, the machine status 0, it may be going towards capital S. In that case, inventory provision is on, the production is on. After reaching capitals, when you are coming down, the machine is off. Okay. But when you touch the small s, you switch on the machine. So in this region, when the inlet level between 0 and s, the machine status value is 1. So we can see very clearly they are not just you can take all with this. This 0 1, here also 0 1, then I can simply ignore it. The hall size is kept in, whatever be the event level, it will be 0 to kept in. The arrival phase, when the people are coming, arrival is coming, so it can be any phase 1 to m. But production phase, only when production is on, it will be 1 by n1. And for this case, please note that I have got an important rule I defend myself. I got a very a horizontal bar. There are many vertical bars. You can take value one here, another value here, another value here, and you could go on. By integrating the horizontal lines, I restrict myself that I should not cross the border. If I start from here, I can go anywhere, but I should not cross this horizontal bar. I can choose any value here, but when I come here, I should not cross. Similarly here also, when I hear 0, I can't have any service phase because when inverted 0, no service is being performed, so there's no service phase. But when there are items, you are going to serve, you want to service any instrument, any item, so the phase will be 1, 2, 3 up to n2. So this is the interdependency of this. I am going to use one simple trick. I start from here, I take one vector, one value here, another value here, another value. The top line I call the first value as I go to an order set. Then 0, 1, 1, 1, 2. This is the second one. Similarly, I can just collect the tuples. So this 1, 2, 3, 4, 5, yeah, 6 tuple. I go to collect 6 tuple. That way I would have a vector state space, and I can order it as I told earlier. I start from the top 1 by 1. When I exhaust all these things, then I go to the next one. When I exhaust the second one, I go to the third one. So this way I can make a small ordering. Therefore, I need this order only for writing down a matrices, unless otherwise I don't need it. So I use a notation like this. I start from L, next level, next level, next level. Here I export all. What are the states are available for this? I use. Then I come here. I change the state to next level. So this way I can have an ordered collection. Okay. Then I am going to write a transition called matrix. I am going to call P sub a hat of a process. This is a dimensional, and I am going to write this is a tridiagonal. You can easily understand that if you are having one item in your stock, when there is a production, it goes to 2. If there is a demand, you are using it, it goes to 0. Therefore, this transition plot is a tridiagonal. There are some advantages. Otherwise, it is very difficult to solve this problem. Now I am going to define this matrix. Please note that the 0 is not just one single value. It's a vector of 6 values. This 6. So this matrix. This is a matrix. So everything is a matrix here. I have to define it. So for that I need one simple notation. Is for notation I am going to use, I think it's 46, I think. Yeah, I am going to define a binary operator on A and B. There are two matrices. A may be having size L and K, LK. B is an arbitrary matrix. There's no restriction on its levels. I put a cross product. This is called a Kronecker product. This is defined by taking the first element, second element, and so on. At each position, you write the B matrix. That means you're going to multiply this. So this axis is going to increase in manifold. Suppose this is M into N, M rows in column. This will be L M by K N, a large matrix. This product is defined like this, and a Kronecker sum is plus circle A plus B equal to a Kronecker product of A and I identity matrix plus I Kronecker product B. So this is the notation I need. So in order to define A0, please note that I am not going to explain everything, but I am going to say only as just indication. A0 is actually moving from 0 to 0. That is, they are not moving actually. Your the barcode change. Previous state is 0, next state is 0. So this is actually given by this. Now you can see the use of Kronecker product. The idea is you can we are using different. Many people are using PROF.C.R.RAO and many scientists, many mathematicians are using different way. But we are using this type of understanding. D0 means there is a transition in the marker-based map, D map. 0 indicates there is a probability or transition within the states, but there is no arrival. And for each entry, you get the P. P is the, what is P?
Professor Arivarignan, you have only 5 minutes more.
Okay, sir. Now I was waiting for your call. Okay, thank you. So I am going to rush through them. Then I will have a way of writing down this, and you can learn it by trying this method. Now all the methods are defined. Now I told you there is a marker chain. Phi is called a 6-tuple marker chain, and its probability matrix is the P hat, and I consider the invariant vector. That is phi P cap equal to pi, and the row sum is 1. Okay. Now with this, of course, this is very difficult to evaluate because this is P is a very huge matrix, and in block partition form, I can write and I can simply diagonal. I want to make it homogeneous, that is everything brought to this side, and this is very difficult to solve, but we are going to solve numerically. But there is one method given by Geber, and this method we use for algorithmic purpose. That is when we want to compute numerically, we use the computer, and we compute a set of F matrices. Using the F matrices, we compute the stochastic vector. So this is implementable, and MATLAB is can be used, but we wrote our own program in Julia, and we are able to compute. And assuming that we are able to compute this, I am going to consider the system performance measure. The expected inventory or mean inventory level is, when the inventory level is high, it's a vector. I multiply by a column of row vector, column vector 1, 1, 1, 1, so that this row vector is added. This is the value for I, inventory level I. Therefore, I compute the mean inventory by summing I into the probability. The expected production startup rate and the expected rate of loss of customers and we consider these parameters and we impose the cost structure, CH, holding cost, production startup cost, the setup cost, shortage cost, and waiting cost, and using that, we construct the total expected cost rate. It is given here. It may look frightening, but of course, this cannot be solved by algorithmic method. We are using only algorithmic purpose, and by taking one simple example, uh, this cost structure, we are able to plot. We produce many graphs, many plots, small s here, capital S. This side, for various combinations, the total cost, expert cost rate is like coming as a ball. But what does it mean? The expert cost is convex. So capital A is 2, capital A 3, capital 2. So there are 3 surfaces. The weighted horse is 2, weighted horse is 3. For all the 3, the total cost rate is a convex. So with this, I cannot claim that this is always convex for all combinations. But our idea is to show it is computable. We are given the algorithms, it is computable, and for from our experience, it always comes out as a convex function, but no guarantee is given for all values. But we are able to demonstrate there is a convexity terms. So we presented what is the sensitivity analysis when the cost changes, the parameter changes, how it behaves. So a large number of tables are produced, and of course that will be given to the publication. But here I am just showing only this. So literature, you can always Google it. Nowadays I do not give literature because it's always changing. People are working on it and people are getting new results. Why do you study about 1999? But there are 2004 or 2006, 10 also there. So 2011 is there. So people are always finding the new results are coming in. So it's better you Google it or using your institution website. You can get the latest research paper. With this, I am going to stop, and I thank Professor Azadigaru and Professor Vittal inviting me to stand before you. Actually, I am sitting in front of you. I was thinking to present my work, and I hope some of you we may be getting interested in this, and that will be the purpose. Thank you.
Thank you. Take any question, if it is, you can contact him with an email address. So now we have the Professor Rasa Reddy sir. We will thank Professor Anbadade for excellently presenting, starting with the Markov chain 0-1 state to getting to Bernoulli distribution, and then analyzing these results from theoretical to the numerical analysis, and then restricting into elementary but powerful ideas of the Markov jump process in the discrete analysis. Thank you very much, Professor.
Thank you, sir. Thanks to Professor Azadigaru.
Thank you, Dr. Arvind, my good friend. Meaning to all of you, next lecture will be my Professor Arvind, sir. And I'm happy to introduce Professor Arvind, sir. Currently, he's professor in mathematics.
Praveen, sound over it.
I'm currently a professor in computer engineering.
Not audible.
Dr. Venkateshwaran, your audio is not working. Yeah, it is not audible and it is noisy. Please check. For the past 5 minutes, it was like that only.
Correct, correct. Mr. Venkateshwaran, are you able to hear me?
Yes.
Huh?
Audible.
He is audible, but sound is coming.
Now also some noise is there.
Very much. Venkateshwaran. Now see that?
I think it might be connectivity problem. Please check.
Hello? Mr. Venkateshwaran. Ravi, அந்த ஆஃப் ஸ்கிரீனை கொடுத்து தெரியுதா சார் அவங்களுக்கு? அவங்க ஸ்பீக்கர் தெரியும். Are you able to hear me?
Yes, sir.
You are able to hear me?
Yes, sir.
Yes,
Yes.
sir.
I will start with my lecture. See.
Sir, now I'm audible, sir.
Yes,
Yeah.
you are audible.
Yeah, now you are audible.
Yeah, yes, sir. Very good evening to all. I'm happy to introduce Professor P.R. Vittal, sir, who is going to give the next session. I'm happy to introduce sir. I've been already worked with Vittal sir in research, and I've been got my PhD. Sir has been completed his education PhD from Math Science, Chennai. Sir has his PG MSc in Mathematics from Chennai. Sir is having the present academic appointments as the visiting faculty, Institute of Chartered Accountants of India, visiting faculty at Institute of Financial Analyst, visiting faculty at Madras School of Management.
Yes.
Also visiting scientist at Indian Statistical Institute, Bangalore, Bangalore, Calcutta, and Delhi. Sir has been published more than 40 research papers in reputed national and international journals, especially in Springer and elsewhere journals. Sir has been attended more than 50 conferences in various parts of country. Sir has been having a different level of publications, and also as a professional activities, Sir has been involved as a statistical analyst in a World Bank project on water and sanitization improvement project for Karnataka state. Sir is also fellow of Tamil Nadu of Academy of Sciences. He has been guided more than 10 students, MPhil and PhD. Presently, he is advisory for the students for the University of Madras. So, Sir has also authored the books for chartered accountants, for BA, BCom level students, for CA in terms of business mathematics, business statistics, calculus, algebra, trigonometry. Has been given plenty of authored plenty of textbooks. I'm happy to introduce here you, sir, and I request you to take over the session, sir.
Thank you, thank you. Praveen? Right. Please. Praveen, see, I'm really very happy to be with you on this day because, you see, I'm associated with the War Society of India. When just like Professor Venkateswara Rao introduced me to war, I just went to the War Society of India in a conference at Srinagar in 2013, and I gave a lecture. Much to my surprise, they have selected my paper as the best paper award at the age of my 75. I am really thankful to the War Society for encouraging me to pursue my research. And then even now today, yesterday I've been informed that I have to give a talk here today. I prepared the talk and then I am presenting the talk to you. Now, my association with Professor P.R.C.R.RAO started with this, in an international conference when he was talking about population analysis. One of the professors who presented the paper told him that always in a population, the first child is the most intelligent, but not the second child. C.R.RAO was so curious enough, immediately put the question, if the second child is not the intelligent, then which child will be the next intelligent child? He said that, I do not know whether we are more than 2 children. If the next child is to be intelligent, probably it will be only the 6th child according to his investigation. And C.R.RAO stood up and said that I am the 6th child of our family. And naturally he said that C.R.RAO is the most intelligent person pursuing in statistics associated with mathematics at the Institute of Statistical Institute, Calcutta, and then abroad, and so on. Now, C.R.RAO introduced many results, especially Cramer-Rao inequality, Loeb-Bechtel theorem, generalized inverses. His emphasis on mathematics is much higher level, so as to say, because he has a good background in mathematics. Professor Krishnamurthy and Professor Arivarangan, both of them presented paper. Fortunately, I have been asked to be the chairperson for this session. Professor Krishnamurthy gave a very nice talk on Markov chains and conducting the queuing theory, and then he introduced a semi-model, and then latecomers can enter into the chain. He did not come from the beginning, and also can give out, and then he introduced the transition probability, which are very wide applications in insurance. Professor Krishnamurthy, if you are listening to me, I'd like to tell you that in insurance, premiums are taken at various levels, and then they also discontinue at various levels because of death or some other reason. So such models could be analyzed in continuous process in insurance model. Similarly, Professor Arivarangan considered the inventory model. I see that the actuarial science possesses several problems that are connected to correlated processes. Not only in queuing theory, in finance, we have number of problems wherein the could be correlated, and number of papers now are appearing in Springer Journal on correlated continuous process. So in my talk, I am going to give you only about compensation function in a continuous time, continuous space process. So, Mr. Praveen, move the first page. Praveen? 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 Right. See, I introduced the concept of what? See, basically, I want to reduce my time because due to unfortunate cases, the others have taken a lot of time, and people who are listening to must have patient enough, especially associated with statistics, mathematics, and operation research. Basically, I start a problem of heat conduction here on. In how the temperature varies at every point of the heat conduction of a rod, and you always can insulate the temperature at one end at 0 level. Now, this has a number of applications, even though this is a deterministic process on heat conduction. It has been borrowed down to method of images in mathematical statistics and operation research. So also several models have started coming in stochastic processes. Now, I'm going into how these processes could be associated with Markov process, jump probability, and further to the differential equations for the probability distribution. Now, it is difficult when you introduce the boundary condition. Now, solving ordinary differential equation will always be much easier rather than there's a restriction for the initial condition or boundary condition. Most of the real life problems are concerned with boundary condition. Now, how to solve a random process with boundary condition is the main question of consideration in my talk. Earlier, we used a number of papers use Richard-Bellman technique of embedding. Now I thought, why not introduce Nielsen technique of compensation function to study such process? Basically, all those who are done through stochastic processor should have gone through Kolmogor's forward equation and Kolmogor's backward equation. All the Richard Bellman technique wherein the boundary conditions are embedded into the process are associated with Kolmogor's backward equation. All the problems compensation function technique as introduced by Nielsen, who was a professor in Rochester, is Kolmogor's forward equation. There are enough problems still to see is these two processes are identical, equivalent. Can we go from one situation to the other situation? What are the merits and demerits of such process and so on? Now I go into a process directly into the stochastic. Now I consider here a process xt that is called a stochastic process. In the case of a dam, it represents the level of the dam, say at Metu, or in the case of finance, it look into the risk level, or in the case, despite of the neuronal electrical field within the membrane potential, it is going to cross the level and so on. Now this x naught is the initial content of the dam, and there are random jumps facing both positive and backward direction. They go into m naught. So what I now do that, I now study this process wherein we are going to make use of the method of infinite images. Now when I use the method of images, this is called the heat conduction equation with a boundary condition that V of x0 is equal to f of x. This f of x is nothing but the initial temperature of the rod. Now it has been well known that for such a process, the solution is given in this form. This is the Gaussian process solution, where mu is called the source of strength introduced initially, and negative source is minus mu. It is only one barrier is there, is a semi-infinite rod. Operation is done at x, the initial point at the x is equal to 0. The temperature is always kept at 0 level at that. Therefore, Vx0 serves as a boundary. Now, if I introduce two boundaries, both the left and right, we now introduce that say V0t is 0, VAT is also 0, A is the length of the rod. For such a rod, now it has been shown by the method of images, the solution is given by this. Classically, the question comes, when you have a heat conduction in a rod, is it possible to find out the temperature at any point of the rod? Either it is an infinite rod with semi-infinite rod with x equal to 0 as a barrier, or a finite rod at x equal to a and x equal to 0 as a barrier, whose solutions are well known. Now, these solutions are obtained by using the technique of method of equation. Those who know physics might show very well that how these solutions generate in a Gaussian form using the method of images. Now, what we are going to do that, can we extend this to stochastic processor with diffusion, right? And the jump process converted into a diffusion process. That's my question. Now you see, I introduced the forward equation to such a process. How do you consider the forward equation to be a process? Now at time t, where the particle is, and it has come to the position x dash, and then make a jump and come to x. This is a free-bounded process. X could be anywhere from 0 to infinity, and is a single barrier problem. Initially, the source function is at x equal to 0, and it is a delta function. Now, for such a function, we know that the Green's function, that is the solution of the unbounded process, is given by gxt. Now, we have explicitly given the solution of this process. Now, it is well known, any standard textbooks will have this. Now, for this, if I take the Laplace transform with respect to the phase variable x, I immediately convert this transform function into an algebraical a differential equation. Now, this differential equation can easily be solved, and for this, the solution is also given. This differential equation could easily be solved. The solution is also given 0.3.5. Now, this is well known. This is well known. What now we are going to do that? Can you convert this solution into a bounded process? Now, how do you go from the similar to the method of images in solving such a problem is a question. Now, for that, what we are going to do is that we consider a compensation function. Method of images is now extracting a virtual image on the left side and then taking the boundary out. Now the compensation function is allowing the process to proceed through the entire line whose green solution can easily be obtained, and it will define the cause CXT, then automatically the solution to the first passage time, the problem is known. The first passage time is also able to find out what is the temperature at X at time T to be at X, what is the dam level, what is the rest level, how the company can maintain is the reserve. All these things could be solved with the help of such a compensation function, provided you introduce the density function with a suitable probability function. Now what I do that, I consider the FXT in this form, and the CXT turn out to be a generating function of this form. And now my question is, how I am going to, CXT takes as a correct to remove the boundary. How to find out my CXT is the question. Now, in order to find out CXT, what we see that it should not go the negative direction. When you remove the boundary current from the restrained process to unrestrained process, this is allowed to see it jumps from X dash. It jumps from X dash to X, where X could be in the negative direction, and therefore we are cutting off from the solution, and hence we introduce the minus sign. Now, the F naught is the direct delta function with intensity mu. And the CXT which we want to determine is completely comes in the terms of the convolution form of both time variable and the space variable. Now, for which I know the solution FXT in this form, where Fxk is nothing but the position of the particle after the kth jump, and it is going to be the convolution process. Now, what we do that, we find out Fx and we find out Ck. Ck is found out in terms of Fk minus 1. That means that when the particle has come to within the boundary and take a jump and comes outside the boundary. When it comes outside the boundary, it should be negative. That is why we introduce the Heaviside function. H of x is called the Heaviside function. The negative direction shows that it is being prevented earlier in the constraint process. We are removing it. Therefore, Ckx is nothing but the first passage time when the temperature level is going to become 0. Now, for that, what we do that, Ck plus 1x we introduce. Now, Ck plus, since we know the Ckx, we write down the Ck plus 1x, and then Ck plus 1x, we have to go into the process. And if I know Ck plus 1x, without the f functions coming there, now that I have eliminated. In Ckx, the f functions come there, do a lot of mathematical algebra in order to write Ck plus 1 in terms of Ck only completely. So it is like a recurring process. It is like a recurring process. And now if I want to go to the diffusion, what I do that, allow the jumps to large number of random jumps are taking place, and so the average jump size is 0, and proceed to the limit as gamma tends to infinity, such that the second order movement becomes a finite, and hence I can find out the solution in this form. If I expand, I can find the solution to this form, and it is possible to invert this by Fourier transform. If you invert this, you arrive at this equation. We know that this is nothing but the diffusion equation. Once we arrive at the diffusion equation, now you see that you have the CXL. We have CXL. Here also I proceed to the limit as gamma tending to infinity, mean tends to 0, and the variance is finite. Then I can find Ckx. When I find Ckx, ultimately I now know my CXT is a separable cost. My CXT is nothing but a delta function at minus x naught and at t to the 0. Therefore, essentially introducing the method of images for a deterministic process is equivalent to introducing the compensation function, removing the boundary, and then introducing a negative source on the negative side at minus x naught at time t to the 0. So, if you remove the negative source at time x equal to 0, my CXT is going to be the first passage time. That means when the insurance company is going to be doing, or when a dam is going to be overflow. All these things are called boundary value problem, and we can determine using the CXT. Now, the question comes that the process of interest is now this, except t is now 0 to t. Now I find the Laplace transform, take t1, t2, etc. As the times at which the Python jumps are going to take place is a homogeneous process. Now I go into the two-barrier problem. When I go into the two-barrier problem with the finite state, I introduce a barrier at x equal to 0 and introduce a barrier at x equal to a, and I take the transforms in Q01 dot generating function. look at the generating function, one variable is discrete, the other variable, time variable is continuous, position variable is discrete. Now I define Q1, Q2. Q1 is jumping on the ruin side, the negative side of the origin. Q2 side is the overflow side, that is X2 side is the zero. Now Keplerman connected these three generating functions in a very nice form. This is called the Keplerman's equations for determining the generating function of overflow or emptiness of the dam, or generating function of the risk reserve being enormous, or the generating function of the company being ruined. This is called the generalized reward identity. In fact, I like to point out Numerical Ward, who derived the sequential analysis to test the hypothesis and to determine how many elements you should have in a sample plot in order to draw the conclusion. He worked out in sequential analysis, but later we have borrowed that idea to derive this in terms of the stochastic process. That's why it is called the generalized world identity. Unfortunately, Abraham Ward, when he came to the Chennai to give a series of lectures at the Madras University, went a tour to the Ooty for a car by a plane, and plane crashed, the entire family died. So that gives me the more sympathy towards his work, and it opened my mind to go into the generalized world identity, not only with a constant barrier, but also with a moving barrier and stochastic barrier. Now you see that the decomposition of Wiener comes. See, once you find out the generating function, Wiener of decomposition comes, and by Wiener of decomposition, what we can do that 1 minus Z5 could be split up into two forms. This is the product of the exponential term, the positive side and the negative side, and then we know, using the Wiener of decomposition, we are splitting Q0 and Q2 in terms of Q1. We will be splitting Q0, and we found out Q0 and Q2. Also, we can find out Q0 and Q1. We use Lowry's theorem of complex analysis to find out what is Q1 and what is Q2. If we are able to do that, we are generating the function. That's why we now say that the expected time of crossing the barrier in terms of the fundamental identity of the world and the generating function consisting of Wiener compositions we have to get this. Finally, in continuous time also these results could be arrived. Now we go into the generating functions in continuous time. What we see earlier is a discrete time. We go into the continuous analog, both space variable as time variable or continuous. That is why I refer to going to the actuarial size for a work similar to our Krishnamurthy, Professor Krishnamurthy and Arivarignan. They find that they could easily be extended very easily for continuous process and continuous time. Now, this is the fundamental identity for the continuous process, continuous time. But in order to see that the Poisson jumps or number of jumps is considered, we are able to convert the jumps into generating function for Q0t in terms of Q0 and Q1t in terms of Q1. So what we do that is Q1 and Q2 are nothing but the probabilities jumping to the negative interval or positive interval truncated from the point A to the infinity. Now, we can easily see that how this Poisson nature of the jump process, independent nature of the increment, hence in dealing with this situation, it will be adequate to consider the identities regarding the Q's irrelevant to the Markov jump process and so on. Now what we do that, we consider the forward equation for the jump process for a two-barrier problem. Now initially the particle is at x0 with the initial intensity is mu. Now this is the condition Wx0 is 0 on the negative side for the origin or above the positive side above A. Now what we do that we write down the stochastic process for this Markov jump process and we introduce the barrier counting condition C1xt and C2xt. They remove the current and thereby we can define my C1xt in this form and C2xt also in this form. This shows that how it jumps to the negative sides. Therefore, the first passage time for company doing how this crosses the barrier again. Therefore, it gives an alert to the company that they have to declare bonus or dividend to the shareholder so that there will be a restriction on their reserve. The question is essentially determining C1 and C2. If you determine C1 and C2, you are able to determine the control of every one of the process. Now the question comes, how do you find out the generating function in terms of the Green's function? To find out the Green's function in terms of C1 and C2, what I do that, I go for Q0 SZ and Q1 XZ and they are nothing but the transformation for the homogeneous positions of jump process, and thereby say I get my C2n. C2n is the nth image. Now you see, you are introducing the barriers at x equals 0 and x equals a. Therefore, when I introduce sources and sinks alternative like method of equation in studying the temperature at any point of the rod, I now introduce the compensation function. The compensation functions are nothing but the negative of the jump. That's why we introduce the minus sign, and the negative of the jumps, when you evaluate, you get this algebra, and thereby the C2s is ultimately calculated in terms of the inferior C1n minus 1. We are going to proceed to the conditions, and ultimately we arrive at C2n in terms of C1, right? So if you have a mirror on one at the one boundary x equals 0, you can have a mirror at the other boundary x equals a. The reflection on these two boundaries are nothing but the passage time to Rugin, or the passage time to what you say crossing the overflow of the dam, and so on. Now, since you find C21, first image is this. Similarly, you can find C1 also, and I can find out C1 also in terms of this, and ultimately I go into the limit of gamma. Okay? Now, what is the diffusion is from jump process going to diffusion process is very interesting. So you are going to give number of jump, larger number of jumps, smaller size, and ultimately this jump process turn out to be diffusion process. Diffusion process is equivalent to the Brownian motion, and Wheeler process, or otherwise is equal to OU process. And now we see that when we proceed to gamma tending to infinity, ultimately I now see that the density is going to become a delta function. Now the density is going to be delta function, and my first image is going to be at minus x naught, and initially the particle is at x naught with the intensity mu. So I am connecting C11 in terms of the initial image, and therefore introducing an image at x equal to x naught is equivalent to have a negative strength of minus mu at minus x naught, and similarly at minus mu at x greater than a, and so on. We see that the C1n is ultimately given by an Heaviside function. Heaviside function means that it is going to take the value 1 if minus xn is greater than 0 or xn is less than 0. Now you see I am finding out C2. Since I find out C2, now it is my easy question now to see that how these jumps are related to method of equation. How these jumps are related. Now what I do that, I go into C2n, and ultimately I find out my C2n is nothing but mu cap in the first image, is going to be the second image, is going to be the right hand side this first image, the left hand side the fourth image, and so on, because they are taking place mirror after mirror. The images are going, the number of images is going to be infinity, and I proceed and couple them all. Ultimately I see that they are going to be in this format. All my images are generated. If I join these images together as a generating function, I get ultimately the solution to the CXT, and since I get the CXT, and ultimately you solve the problem with the value. Now the great advantage of this compensation function Kielsen is that it not only gives the boundary crossing probability, it also gives the position of the particle at time. In other words, what I like to tell you that what is the level of the dam, how much level water is there in the dam, that we can find as a stochastic process. What will be the risk reserve of a company, that you can find out this process. Or what will be the neuron level in the electric input potentials of the brain functions, that you can find out. All these things are now generally models of the stochastic process in terms of jumps and diffusion, and with barriers are introduced, we can solve them through compensation function. We have earlier solved number of problems through what is called the Richard-Hillbrand technique. This is the problem I am presenting, that they can be solved through compensation function technique. And now the question, the merits and demerits for every system. If you go by embedding method, it is easier because the boundary is put into the embedding equation of Richard-Hillbrand. Automatically when you got the solution, that we get the solution for the barrier cross. But whereas the compensation function is concerned, it might be easier to go for the moving boundary. I can allow the boundary to move with time. I can allow the boundary to be stochastic in time. Then also we can find out the solution of boundary crossing and position of the particle at any time. So whether the compensation function technique is used in studying the process to find out the fluctuation of the particle between the two barriers or outside the particle, first time it is going to drop, or the Richard-Bellman technique, all both could be solved either for the time-dependent or time-independent solutions and so on. Ultimately, we now find out when time-dependent comes, it is much easier to apply the compensation for technique. When we know that it is necessary the jump should take both forward and backward. In order to say, in the case of a dam, the water goes out of the dam, that is the outgoing side. Because of rain, water comes to the dam, that's the input process. So the input process and the output process both simultaneously take place, and as Professor Krishnamurti said, it is to be assumed as the exponential form. If we assume the exponential form, it is easily separable. But what we have done is that if it is in general separable form, not necessarily assume the exponential form, then also the solution is part of, and our solution matched with that of Bayes-Szabo. They have written in connection with about heat conduction in a different paper. We have generalized many results, and these results also agree with them. And ultimately, what basically I have said is that the solution comes in terms of the Green's function. See, Fxt is called the temperature at time xt, or the position of the particle at time t in a random process, and G the Green's function. See, n both the number of jumps either to the positive side or the negative side, x not the initial position of the particle within the barrier. That means we introduce the temperature initially at one point x naught with intensity mu. Therefore, in a stochastic process, we can always find out the Green's function of the process during the convolution, and therefore we not only find out the boundary crossing probability, it is also possible to find out what will be the position of the process at any time. These are all the advantages of the compensation technique, and we know ultimately in terms of the probabilities and functions, we ultimately find the Green's function is nothing but the probability space function. Whereas, if we go into the technique of invariant, it is possible to find out the Laplace and Fourier transform for the time and space variable. Inversion process is very difficult. It is not possible so easily to find out, therefore, find out the moments of the process there, but not the probability. But here, not only the moment, the probabilities can also be determined with help of this process. So, essentially to summarize, I want to finish in time, therefore, essentially to summarize, what I like to say is that simple diffusion process or the boundary rod problem with the initial temperature at some point is considered to find out the temperature at any point by the method of behavior. Now we consider a stochastic random processor. We allow jumps on both the direction as an insurance company inputs and output, or in a dam, the level increases and so on. And for such a random process, we introduce a boundary command called the compensation function into the forward equation of the different stochastic dynamics of the process. Then we find out the boundary current in order to the delta function of the initial image. And once you determine the delta image, then solution is equivalent to the solution of the Green's function of what the method of images say. Ultimately, the deterministic process of method of image helps us to go into stochastic processor, but the most powerful technique is the generating function technique. This generating function called the Green's function gives you the complete history of the process in terms of the probability space and not in terms of the transform state. That's a great advantage of this Laflamme technique. We are also now studying these problems in the correlated process. Professor Harivaran said that the Poisson events should also be considered as the correlated point events in its process. Yes, now we are now removing the Markovian condition, the Poisson condition to remove. That means we suppose if that in case of a finance, say in insurance company, there are two types of accident. One is the building collapsing, the other one is car collapsing. Even then, a person who is sitting inside the car or inside the building might die. Therefore, the car insured or the building insured is associated or correlated with the person who has insured independently. Hence, the connection between the two types of accident ultimately be connected in terms of the person who also dies. Hence, the correlated process could be determined in terms of the Green's function. There are much more papers that are coming into the function. Now, what Gilson did is somewhere in 1962, gold is always gold, you see. Therefore, even currently we have connected these processes in 2019 in one of the published paper, how these elder results, now older results could be connected with new idea and coming into generation function technique of finding out the solution to Markov process or OU process and so on. Therefore, a lot of new works are now coming into the process, and students who are interested can go into the literature and find out still a number of problems, the correlated process as Dr. Ariman pointed out, are available. You see, they are open problems. You can solve those problems and so on. Essentially, the question is that how to solve a bounded problem into an unbounded, converting into unbounded problem by a method of images which is equivalent to the compensation function. The compensation function is now equivalent to a probability generating function in the probability space, where the method of images is equivalent to the physical nature in the heat conduction. So we have connection between the method of images and the compensation function. That's why given the title of the paper is on compensation function and the method of images, how they are connected, how they help us in determining boundary crossing probability, not only boundary crossing probability, also the position of the particle at any time inside the barrier also. When you are playing the gambling, what is your level of the asset at the time of the gambling process? Either you are not ruined or you are not totally prosperous. All these things should be analyzed with help of the compensation functions and so on. There are a number of ideas are coming into the picture, and it is only the younger generation to take interest in proceeding in those problems. Yes, work hard to get the solution into this problem. I was also telling the other day to Professor Venkateswaran to proceed on Venkateswaran, one of the good students he came across, and definitely can pursue all these things. Further, he can continue his research. I wish such students come and proceed. And we are all old people. I am now about 83 years. So we may not have so much of strength as we used to be in those days. Again, I wish Venkateswaran and his group to pursue those problems, and people who listen to the students. There are many engineering college students, and now I report the heat conduction equation. You study in mathematics, you see, how about heat conduction equations and how they turn out to be diffusion equations and so on. All these results could be connected with stochastic processes. You see how the connection has to be made. Once you understand the connection, you start from a simple problem. You can generalize this to many problems, right? So I wish that the students of this session would have followed little idea about this, and therefore I like to conclude, and I want to see that my talk should be over before I cut short many of these slides, because that the people who are listening to me, and I myself sitting for about 2.5 hours, you see. Now when you are listening so much with all that, you will be very tired. And ultimately I say that we started only with a simple equation on diffusion process and see the method of images is equivalent to the compensation function, how the compensation function enable us to determine the first passage type to either of the barrier, one barrier or two barrier, and we are establishing the generation function equivalence to compensation function is a very novel idea using the procedure of Thielsen and then the generating function. Okay? So go through this, it will be available if you Google the search with Thielsen's compensation function. Probably you might find out number of such ideas. When I was in US, I remember in 1989, I met Thielsen at Rochester. He was a professor there. I've been to Cornell to give a series of lectures there. I went to him, his place, and then met him and also talked about that. And now we introduce a type of barrier called the absorbing barriers and reflecting barrier. Our Krishnamurti spoke about absorbing states. You see, the process terminates for absorbing barrier. Now reflecting barrier means the process redo again. The moment you see water level of the dam becomes full, and again the level decreases and the process continues. So that is called the reflecting process. Therefore, how to modify the compensation function in terms of the reflecting barrier is a very important question. There is a problem called book called Thielsen's probability theory. No, there is a book called Thielsen's probability theory. TC electricity, Thielsen, you see, a number of problems on first passage time. Because Thielsen, the only person who did on compensation function, and therefore I quoted only Thielsen, and that Templeman is also generated to two big ideas of field of techniques. So these ideas of complex analysis might definitely help you to go deep into this problem. So in research level, what I like to tell you that instead of going on the surface level, go deep, then you can find out good results. What about, and you cannot realize their values. So then you will enjoy in picking out these wells by going deep. So I will stop with my talk and then ask the chair to go into the further proceeding of this. Professor Praveen, இது கொண்டு போயிடுவா Praveen, put on. Right. So I would now like to tell you that he's talking to me yesterday night only. Professor Renigar asked me to give a talk a day. Otherwise, my question is only on the chairing the session. So I'm really happy that with many seniors are now here, and many students will come forward. I'm really happy on the birthday of Professor Renigaru. I've been asked to give the chair session, also give a talk here. So my best wishes to Professor Reddy.
Thank you, sir. Thank you. Thank you, sir. Thank you, Dr. J.R. for participating in my lecture and your lecture presentation also. Okay. So now, under 5 minutes, we have today's student program is completed. Now, we have another 5 to 10 minutes for the class. I think time. So, immediately we start ISPS in individual ISPS members
Thank you very much, Professor Reddy, and all of you patiently getting the last over of the match. Right. Thank you very much.
Sir, voice is not clear. Sir, there is a lot of disturbance in the voice.